Right, so presumably you can see my slides and hear me well.
Yes.
Great. Yeah, so hi everyone, I'm Edward, I'm a postdoc in the group of Nicola Mazzari, and my talk, in contrast to Andrea's, which was focusing on the sort of theory and the ideas behind these Koopmans functionals, I'm going to start to delve into some of the practicalities when it comes to running these calculations. So what are the implications of this theory, of this orbital density dependent theory, for what the code has to look like and what sort of equations we have to practically solve, and then what does it look like for you as a user when you have to run these calculations. So yeah, so this is already what I've said, so hopefully give a clear idea of what Koopmans functionals are, and I want to really emphasize how they differ from a standard semi-local density functional theory calculation, and in terms of the implications this has for running these calculations, and also start to talk about the codes that we use to run these calculations. So like Andrea has outlined, the goal of these functionals is to obtain spectral properties, or what I mean by this, the charged excitations, so the process of adding or removing an electron from a system, but doing all of this within a functional theory framework. And as he showed, and I'll go through this quickly, that the core idea behind these functionals is that we want to impose this condition that our eigenvalues that we obtain, here I've laid this epsilon I Koopmans, these should be independent of the corresponding occupation of the orbital. So I've called the occupations are labeled here Fi, and these should be equal to the corresponding total energy differences when you actually remove that an electron from that orbital. And so, as Andrea showed, this is sort of related to this idea that's come up throughout these 3 days about piecewise linearity, or more accurately, the violation of piecewise linearity by semi-local density functional theory. And so we can see that here in this plot, if we've got some sort of semi-local functional which has a curvature to it, here shown in orange, then the derivative of the total energy at this point here, which corresponds to the HOMO energy, is not going to be equal to the total energy difference. Whereas if we had a function that was piecewise linear, then the eigenvalue or the derivative would match the total energy difference. And we know that density functional theory, total energies are well defined, but the derivatives ultimately only refer to our auxiliary non-interacting cone-Sham system. And so really, we've got no right to talk about eigenvalues as something that are meaningful, or interpret these sorts of band gaps that you just extract from semi-local DFT as something that we really rely on, but we can rely on total energies, which are much more rigorously defined in a DFT framework. And you also see this practically. So if we here look at data, so this is calculations across a set of 100 different molecules, and here I'm looking at the ionization potential. So the ionization potential is the energy that is required to remove one electron from the system. So this is the same, it should be the negative energy of the HOMO energy. But if we just look at the PBE HOMO, this systematically underestimates the ionization potential when you compare it to high quality quantum chemistry results. Whereas if you look at total energy differences, so this is just still at the PBE level, we get energies that line up very well compared to quantum chemistry results. So I think this is the point, and this sort of comes back to one of the earlier questions, was about, you know, what is different here from the density functional theory, and why do we get so much better results? So the ingredients here to Koopmans functionals are just simply this idea that we want our eigenvalues to be equal to total energy differences, and then just the energy, and then the only other ingredient is the physics that's already contained in total energies in density functional theory. And so just with those ingredients, we can get spectral properties very well. And so contrast this with, say, the example of meta-GGAs or hybrid functionals, where you're starting to add other quantities into your exchange correlation functional, like the kinetic energy density, or various non-local the Hartree-Fock energy. And so here, just to reiterate, the only ingredients really are those are the base functional and then this additional condition that we want to impose, which we call a generalized piecewise linearity, because what we're doing here is that we're, actually, I might just get onto that slightly later. I'm getting ahead of myself. So what these corrections actually look like are the following. So what we want to do is we want to have eigenvalues that are explicitly linear in the, we want eigenvalues that are independent of the corresponding occupancies or total energies that are linear in the occupancies. And so our correction takes the form of this sort of equation here. So for a given orbital, let's say I'm here on my energy curve, for a given orbital, I want to remove any erroneous dependence that that eigenvalue has on its corresponding occupancy. So that's what this first term does. So we just remove any dependence of the total energy due to eigenvalue dependence on its corresponding occupancy. And then in place of this term, because we've removed this energy, we add some term that's explicitly linear in the orbital occupancy. So f of I is the orbital occupancy and eta I is the slope of this term. So it's some constant that I'll talk about how we did work out what that constant is later on. So this is the sort of the general form of the correction that we want to apply to orbital I. So here is the full Koopmans functional now. And now what we've got is we've got that same correction here on the right, but now we're going to apply, so then there's the sum over all the different orbitals. So we're going to apply this orbital by orbital to every single orbital in our system. And so here we've got some base density functional theory. So this is like our PBE or LDA or PBE or sort of the PBE sol, for example. And so we're taking this density functional and we're just adding this additional term that orbital by orbital, we're removing this erroneous dependence of eigenvalues on the occupancies and adding in some term that's explicitly linear. So this is kind of like DFT+U in a way, because again, we've got some base functional and then some correction, and we just differ in precisely what we're trying to correct. So if we look at this functional, this general functional form, there are several very key differences that this kind of functional has got to a semi-local functional that we all know and love, and you'll be used to performing those sorts of calculations. Well, one important thing is, firstly, we get different flavors of our functional. You will have, Andrea mentioned some of these briefly, and I'll sort of enumerate them in detail coming up, but this is all to do with what precisely we choose for this slope to be. And this ultimately affects the eigenvalues that we obtain in the band structures. The second key difference, and again, Andrea touched on this, is now we have an orbital density dependent functional. So no longer is our function, do we have a functional that's just dependent on the total density, but now we have a dependence on the densities of individual orbitals in our system. And so, yeah, we'll talk about that too later on. And finally, and this is the one ingredient that I haven't sort of mentioned here and explained here in this equation, is we've got these alpha parameters, which are called screening parameters. And these account for the effects of screening in a post hoc way. And it's one of the most expensive steps in a Koopmans calculation is working out what is an appropriate value for these screening parameters. So for a large part of the remainder of my talk, I'm going to work through these three different points. So firstly, the different flavors of Koopmans functionals. So like I said, we've got this 1 degree of freedom. What should be the gradient of this linear term here in our functional? So we've got a couple of choices. So the first choice, and what we call the Koopmans integral approach, is that we're going to choose our this gradient such that it's the difference between the integer points on this curve. So there's where the occupancy is 0 and the occupancy is 1. And so by writing it like this, this is going to explicitly enforce this ionization potential theorem that these eigenvalues should be equal to those that are given by total energy differences, because if we evaluate this guy at either 0 or 1, we get the energy, the total energy at when the orbital is totally empty or totally full. And one of the key things about this base or Ki functional is that it does not affect the total density or energies. And the reason why we can see this is that in the case of insulators, f of I is always either 0 or 1, and so this entire correction vanishes completely. And so then the total Ki energy is going to be the same as the energy that of the base functional. And so the total energy will be exactly the same as that of your base functional. The density will be exactly the same because it will minimize it. So because it's just minimizing the DFT energy. But this doesn't mean that the correction is doing absolutely nothing, because while it doesn't affect the energy, it affects derivatives with respect to the total energy. And these derivatives are our band structure. So the derivatives of this total functional with respect to the orbital occupancies gives rise to our band structure. So Ki leaves the total energy unchanged, but it changes the band structure and improves it remarkably. The other one that we had that Andrea mentioned as well is the KIPZ functional. And so this is exactly the same as the Ki functional, except we've got this extra term here, which is the Purdu-Zinger self-interaction correction. So basically, on top of the Ki functional, we're also adding a Purdu-Zinger correction, which targets one body self-interaction error. And this means that the functional is exact for one electron systems. And now in this scheme, the total energy does change with respect to the base functional. And so you get different total energies, different densities. And so generally, this is a more expensive approach because we need to care about updating the total density with respect to our base functional. There are a few other flavors that you might see if you sort of read literature or look at some of our previous papers. There's the PKIPZ. So this is perturbative KIPZ. And so what this is it's the KIPZ Hamiltonian, but we only evaluate this on the Ki solution or the DFT density. And so basically, like I said, KIPZ is computationally more expensive than Ki because we've got to actually update the density and so on. But we can sort of get halfway there by evaluating the KIPZ Hamiltonian non-self-consistently. The other iterations, you might also see the K functional, which was an earlier iteration of these functionals that was based off half filling rather than integer endpoints. This functional is no longer used. So if you're reading the old papers and you see this functional, I mean, by all means, pay attention to it. But in terms of what we do these days, we prefer to use the Ki functional because that explicitly and because that exactly enforces the IP theorem. Yeah. Okay, so that's the different flavors that we might see of these Koopmans functionals. But now there's orbital density dependence. So here on the left, I've written down our correction that we're going to apply to one particular orbital in our system. And if you sort of write this out, then you get a term that looks like this. So we're ultimately what you're doing is you're not doing these complicated integrals. All you're having to do is evaluate the Hartree exchange and correlation energy on various densities. And the potential of as applied to a particular orbital is given by this functional derivative. And after some derivation, we can basically obtain that these potentials are given, you can write them down, and they're made up of three different parts. So the first part is a scalar term. The second part is a term that has got some spatial dependence, but it's diagonal in the orbital indices. So I and J here are the orbital indices. And And then finally, we've got a non-diagonal part here. And so here, very clearly, we've got a potential that is going to be dependent on the orbital in question. So we've got this orbital density dependence. And specifically, if I now look at filled Koopmans orbitals with the Ki flavor of Koopmans functionals, we actually, this diagonal potential and the non-diagonal potential actually vanish entirely, and all that is remaining is the scalar potential. So here's our potential here, and it's simply just a scalar value. You can see there's no spatial dependence at all. And so at the basic level for the Ki functional with filled orbitals, all this amounts to is that we're going to take individual orbitals in our system and we're going to apply some rigid shifts to the individual orbitals. Note that this is not just a scissors operator, because we might shift different orbitals by different amounts, and also this is only for filled orbitals. So for our empty orbitals, these spatially dependent potentials are non-vanishing. But often what you will see at the sort of first level of approximation, if you just focus on the occupied bands, is that this potential will shift blocks of bands up and down, which is what we want to do, because we know that PBE is, or DFT more generally, gives bad band gaps, for instance. So practically, this orbital density dependence means that our energy is now a functional of the orbital densities, and so we need to minimize the total energy with respect to individual orbital densities. So the way that we do this, or the way that we do this is using the conjugate gradient algorithm to minimize that energy. And actually we do this in a two-step process. So we've got an outer loop, and here we just allow the orbitals to relax in any which way they would like. Obviously still maintaining the fact that they remain orthogonal. But here we just allow the orbitals to relax in whatever way they would like that would lower the total energy. We also perform an inner loop. So here we've got a system of nested loops where the outer loop, we're just allowing them to relax in any which way. And in the inner loop, we specifically focus on ways in which we can minimize the energy if we do unitary rotations of our set of orbitals. So if I get my next best guess of my set of orbitals, I can just mix these together and rotate them. Now note that this operation doesn't change the total density. So if I was to do this algorithm within a density functional theory, this step would have no effect. The DFT functional would not care about the fact that I've mixed my different orbitals together, because ultimately the total density doesn't change. But for an ODD functional, this sort of rotational invariance is broken, and so these sorts of operations become important. And so practically what we do, and you'll see this in the files that we'll look at later today, is that you might see this iterations with the CG minimization with an outer and an inner loop. And for more details on this precise CG algorithm, you can refer to this paper here. So when we minimize the total energy and we get all the way down to our energy minimum, now we have a set of minimizing orbitals. And here is a picture of some example minimizing orbitals. So you can see very specifically that these are localized orbitals. So this is really important. So when we minimize our total energy, this gives us a set of orbitals that are already local in character. And we call these orbitals the variational orbitals. Now contrast this to what would happen if we now take our Hamiltonian in this energy minimum and diagonalize it and look at the orbitals that diagonalize it, these diagonalizing orbitals. And if we do this, then we get these so-called canonical orbitals, and these are very delocalized. And so what we have when you've got an orbital density dependent functional, we've got this duality between these two different sets of orbitals. We've got the variational orbitals that minimize the total energy, and the canonical orbitals that diagonalize our Hamiltonian. And so Yeah, and this is a very important feature of ODD functionals. And this becomes very important. So this is a result that Andrea showed briefly, and I might just delve into it a little bit more deeply. So this is a plot of the ionization potential of various hydrocarbon chains as we just make them longer and longer and longer. So here we're plotting this with respect to the inverse length of our chain. And so here we've got, what is it? The very shortest, and then here we've got polyethylene rather, at the far side. And so, as we can see, if we just focus on the PBE results and we look at the value of the HOMO energy, which and compare this to the total energy difference, if we were to actually explicitly remove an electron and just look at the total energy difference, we see for molecules, we have this big disagreement between these two data points. But as we go from a molecular system into the bulk limit over here, actually these results converge to the same value. And so you might say, okay, this is fantastic. We now satisfy the ionization potential theorem. But actually this is bad news because, and Leo Kronig rather talked about this in the first day, is actually that these two values converge to the wrong value, because what we can see is that if we think about the bulk limit for an individual cell, and I remove one electron from my entire system, then I will have removed delta N electrons from my one unit cell. And so if I now think about the total energy change across all of the cells in my system, then the total energy difference is just given by this expression here, because I'm going to have 1 divided by delta N copies of my primitive cell in my bulk system. And this is nothing less than the derivative, which is given by the HOMO energy. So we can see here that indeed this sort of condition is trivially satisfied in the bulk limit, that our total energy differences match those given by our eigenvalues. But also our Koopman's correction actually is vanishing in this sort of limit. Specifically for orbitals that are very diffuse. So if we imagine now we have some orbital that is diffuse across our entire system, our bulk system, such that basically the density at any one point tends to 0, then our Koopman's correction, if you just write it down, actually vanishes completely, and that would also be 0 in this bulk system. So if we were to apply our Koopman's potential to a delocalized orbital, it would vanish entirely. And so the story is the same as with Professor Kronig, is that here it's crucial to obtain the right limit and the right results in the bulk limit is that we apply our corrections to localized orbitals. And then Koopman's function, so in Professor Kronig's talk, they just said, okay, we'll just choose the highest energy occupied Vanier function in our system. But already we've seen that in our formalism, we already have this set of localized orbitals that we can use. And so the key idea here is what we're going to do is we apply our Koopman's corrections to our variational orbitals. And so this will give us the correct results in the bulk limit. And here you can see when you compare to experiments, KRPZ gives a very good ionization potential of a polyethylene. And here, the reason why these curves don't converge on the PBE result is precisely because we're applying these corrections to the localized orbitals. There are a couple of other features of orbital density dependence that I'll just mention very quickly. One thing is that we now know what the action of a Hamiltonian is on a particular set of orbitals, but we don't know what a Hamiltonian is in general. So this can be an issue to calculating things like inverse photon emission spectra. But I think that's all I want to say about that. Practically, we've got all of these this orbital minimization that has to happen, but often these variational orbitals resemble incredibly closely these maximally localized Vanier functions that we talked about on day one. And so often what we do is instead we use these maximally localized Vanier functions as our set of variational orbitals. And so you'll see later on in these calculations that often the very first step in a Koopman's functional calculation is to do a PBE or some DFT calculation and then do a Vanierization, and then we'll proceed with the Koopman's calculation. And finally, like Andrea was talking about, all of this mess with variational versus canonical orbitals, you might think, oh, this looks like such a headache. Why on earth would I do this? And Andrea's talk really illustrated the point why we might do this very nicely, is the fact that actually this formalism is more flexible, and it's actually a natural generalization in this direction of the spectral functional theories that he was talking about. So it gives us, it's heading in the right direction for something that is going to be able to reliably provide spectral properties like band structures. Okay, so that was orbital density dependence. And now finally, the last of my 3 points that I was going to talk about these technical details with our functionals are these screening parameters alpha. So you might remember that I just said that these are these additional terms in our functional that we need to calculate. So in the context of Koopman's functionals, screening basically means how do we think about that total energy. So more generally, when we write these functionals down, we want to think about our total energy and how that changes as I change the occupancy of a given orbital. Now, this sort of derivative is quite hard to evaluate if I want to include the effect of orbital relaxation, so as to allow the orbital shape to change as I change the occupancy. It's much easier to think about these sorts of derivatives whereby I freeze the orbitals in my system and I just change the occupancies. So for example, you see this in Hartree-Fock. So actually the original Koopman's theorem, and sort of where we get the name for these functionals, is actually a theorem by Challing Koopmans, who in the early 20th century wrote down this theorem to do with Hartree-Fock. So this theorem is the statement that in a frozen orbital picture, Hartree-Fock is linear when it, with respect to the orbital occupancy, or specifically to do with the HOMO. So here you can see this. So here is the electron-electron energy of the Hartree-Fock. And you can see that if I just look at the explicit dependence of this term on my orbital occupancies, it's explicitly linear in the occupancy of my given orbital. However, if actually what's going to happen is when I change the orbital occupancies, I'm going to have these this erroneous dependence that, sorry, I'm going to have additional terms that come into my derivative because of these orbitals will have a dependence on the orbital occupancies. And so you can actually show that as a consequence of this, Hartree-Fock is not piecewise linear in orbital occupancies, but in fact, it's got this erroneous concave curvature. So it's the opposite to what you see in semi-local density functional theory. And so for Koopman's functionals, it's the same. So we wrote down this correction that we wrote down this correction that we said, aha, fantastic, it's explicitly linear now in the orbital occupancies, but that was only in the frozen orbital picture. So what we need to do is we need to account for the effects of screening. And the way that we do this is we do this in a post hoc fashion. So we just assume that we can calculate these total derivatives accounting for orbital relaxation simply by multiplying the derivative in a frozen orbital picture by these, what we call these screening coefficients, these alpha parameters. And so we need to work, so I mean, this sort of looks like we've just sort of moved the problem around a bit. It's just now the question is no longer, okay, how do I evaluate this total derivative? Now the question is, how do I work out what this alpha parameter is? And here we can, thankfully, we can return to our original motivation for Koopman's functionals, and this idea that we wanted our eigenvalues to be equal to total energy differences. And so what we're going to do is we're going to use this idea to work out the appropriate value for our screening parameters. And so to illustrate the way that we're going to do this, here I've just got some imaginary system where I'm looking at the energy of the system as I change its occupation. And specifically, I'm imagining I've got an electron system here with this amount of energy. And if I was to remove an electron from orbital I, so now I've got an n-1 electron system, I'm up here. And so ideally, what we want to have, so these are total energy differences, and these are including the effects of orbital relaxation, right? I've just done a DFT calculation, and precisely, I can just calculate this total energy difference. And so ideally, what I'd like is some linear dependence, because then if I calculate my derivatives, then I'm going to get, so if I'd like this linear dependence, because then if I evaluate my eigenvalues, I'm going to get an eigenvalue that matches my total energy differences. But like we have been seeing throughout these 3 days, semi-local density functional theory gives us this erroneous curvature with respect, so this blue curve here. And so if I'm now, so here we can sort of quantify this curvature. If I look at this quantity, I'm going to call this lambda I. And so what this is this is the expectation value of a Hamiltonian projected onto the particular orbital phi I that we're interested in this case, that I'm filling and emptying. And so here we've got the DFT functional, and also additionally I can add the Koopman's potential. And so this is now a function of alpha. So firstly, if I look at if alpha equals to 0, then this term here vanishes, and I'm just left with the DFT result. And so the gradient of my energy looks like something like this blue curve. And so what I can also do is I could just choose a random guess for alpha. So I could say, okay, I'm going to choose my alpha is going to be 0.6. Who knows? And so I'm going to choose this as my alpha naught, as my guess, and I might get this value here. And so already you might be saying, okay, so now I can probably work out what a good value of alpha is. And so it's actually very straightforward. If we're just going to say, okay, if we're going to assume some linear dependence of this gradient on alpha, then here's the equation. So this is all I need to do, because this basically amounts to working out how this derivative, and this total energy difference compares. And given the alpha here, I've got alpha n, given my guess alpha, this should inform my next guess for alpha. So sorry, here the n superscript is the sort of the guess number, and so this n+1 is not a power, it's a iterative process. So in principle, you could sort of iterate through this process and converge on the appropriate value for alpha. In practice, actually for the Ki functional, this is guaranteed to converge within a single step for filled orbitals at least. So here's our equation for calculating our screening parameter, alpha. And so just to reiterate the different ingredients that go into this quantity, we've got these expectation values of our Koopman's Hamiltonian evaluated on our variational orbitals. We've also got the same expectation, sorry, the DFT Hamiltonian evaluated on the same orbitals. And we've got these total energy of a neutral system and the total energy of our full system where we've removed an electron from orbital I. And so these are the different ingredients that one needs in order to calculate our screening parameters. And so sort of in order to calculate this gives rise to these different sort of workflows that we have for calculating these screening parameters. And so the way that sort of is naturally suited to sort of evaluating those different terms is this workflow here. Now, don't worry about all of the individual details, but sort of just in broad brush strokes, sort of this is what one needs to do. So you do sort of do some initialization process. And then here we've got this process where we calculate our screening parameters. So we want to do this. So what one has to do is you do a supercell calculation, because remember, we're going to need to calculate the energy of the system when we remove an electron from a variational orbital. And when you remove this electron, you don't want it to interact with its periodic neighbor. And so it's important that you'd have a sufficiently large supercell such that these sorts of energy differences are well converged and we don't have the spurious interaction between adjacent images. And so what one does is you could do these various calculations that ultimately you can calculate your appropriate values for alpha. And then finally, once you've calculated your values of alpha, you can do your final Koopman's calculation. So this is the sort of the full workflow in a supercell, sort of just solving in a sort of kind of a brute force fashion, the sort of equations that I've been talking about in the previous slides. The other approach that one can use is a density functional perturbation theory. So like we had for DFT+U, there's a density functional perturbation, DFPT approach that one can use instead of doing these supercell calculations. And this is what Nicola Colonna will be talking about later today. So I'm not going to talk about this in the current talk. And finally, what we've recently shown, and this is the work of a former master student of mine, Yannick Schubert, is that actually you can instead use a machine learning model to predict these alpha parameters, and this makes things a lot cheaper. And he's going to be talking after the break after my talk, so that's something to look forward to. I think Andrea has already mentioned all of these different resonance with various other efforts, but maybe probably what I want to contrast is how the Koopmans functionals differ from or compare with DFT+U, the subject of yesterday. So in DFT+U, we've got some functional which is constructed to correct the local curvature and the total energy of our system. So we had this term that if you sort of write down mathematically, we saw that what it's targeting is it adds this additional curvature in the total energy with respect to the occupations of local subspaces that should in principle counterbalance the erroneous curvature from self-interaction error. In DFT+U, we were applying this correction to selected subspaces only. So we had chose some set of projectors and we're applying these corrections just on those projectors in our system. So often these will be the 3D orbitals of some transition metal element. And these orbitals that you use, well, these are Hubbard projectors. And so often these are atom-centered orbitals. They are frozen, so they don't sort of change as we sort of update the density, usually. And they also form an incomplete basis set, right? Because they don't, they only span the 3D orbitals. They don't affect all of the electrons in our system. And finally, our corrective parameters are these U terms, or V, as we saw yesterday. And so you can calculate these corrective parameters, and we have one corrective parameter per Hubbard site, and they're defined with respect to these charge neutral excitations. And DFT+U, yeah, so sort of that's the DFT+U story. To contrast this, in Koopmans functionals, our functional is, again, it's a corrective functional, but it's designed to target slightly different things. So what we want to do with Koopmans functionals is we're going to remove this dependence of our eigenvalues on their corresponding occupancies. So immediately with Koopmans functionals, we're not targeting total energies, we're really targeting our eigenvalues of us that we extract from our calculation. We want to guarantee this condition that our eigenvalues correspond to total energy differences. We apply these corrections to the variational orbitals in our system. And so this is every single variational orbital in our entire system. And so this is every single electron. So there's not a specific subspace that is subject to the Koopmans functional. Every single electron in your system is affected by these Koopmans corrections. And so exactly, so these orbitals these are these variational or minimizing orbitals that we apply these corrections to. And our corrective parameters, well, this is the parallel breaks down a little, but in terms of practically when it comes to performing a calculation for DFT+U, beforehand you have to calculate your U parameters. For Koopmans functionals, before you do a calculation, you have to calculate our screening out alpha parameters. And these are defined not with respect to charge neutral excitations, as in the case with DFT+U, but they are defined with respect to our charge excitations, the process of removing an electron from orbitals, and then we calculate our alpha values. Now, I think I've got about 5 minutes left, so I might just skip over the results. Already we saw in Andrea's talk that we get very, very nice results that are competitive with quasi-particle, so high quality GW results, so as well as total photo emission spectra. Sorry, I'm going to fly through these. If you're interested in one in particular, just ping them the questions. He already showed these results with respect to getting excellent band gaps with respect to experiments. for a set of insulators and semiconductors. We've got full band structures here again. So these are more recent results where we get all of these flavors get very good band gaps here for silicon and gallium arsenide, among various other calculations. I've just focused on those two, where we get band gaps that are very good with respect to experiments and D-band positions that are good, if not perfect. And here's a result on zinc oxide with our most recent iteration, with which Nicola is probably going to talk about here, where we've got Ki, which is getting a very, very good band gap with respect to experiment. And again, the D-band position, that is quite good. But what I want to do with my last couple of minutes is talk about practically how we run these calculations. So there are several implementations of Koopman's functionals. We've got KCW.x, so this is Koopman's linear, and so this is our DFPT implementation. So this is distributed in Quantum Espresso version 7.1 and onwards. So on your own computer, if you've got Quantum Espresso, chances are this is already installed, and obviously with Quantum Mobile, this will be there. But we've also got the supercell implementation that I was talking about. So we had these different workflows for calculating alpha. So we've got our DFPT version and we've got our supercell implementation. And so this is available publicly. But it's not really enough for Koopman's functionals just to have those codes just sitting there, because you saw the complexity of that workflow, right? They had all of these different nodes that connected together, and we've got these different codes that need to handshake along the way. And there's lots of scope for human error. And so in order to sort of make this a lot simpler, what we did is we wrote this code called Koopmans. So Koopmans is just a code that we've released earlier this year. We've got a website here that you can go to if you're interested in. So the beta version was released earlier this year, and we're about to, well, hopefully in the next couple of months, release version 1. And so this code contains implementations of Koopman's functionals, as well as various automated workflows to run all of those complicated workflows from start to finish. So think of it kind of like so it's built on top of the atomic simulation environment, if you're familiar with that, but ultimately under the hood, it just calls Quantum Espresso. So think of it like a complicated Python script, or hopefully a simple Python script, but a clever Python script maybe is the best way of putting it. So what it does is that ultimately, so Koopmans will just go through the workflow, work out what is the next step. When it reaches a stage where it wants to do a calculation, it'll just call Quantum Espresso or generate the input files that you need for Quantum Espresso, then call Quantum Espresso, and then it will read in the results and continue on its merry way. And so basically think about it as a clever Python script for doing all of these workflows. And so hopefully the key idea is that it doesn't require super expert knowledge. So we'll see later on today in the demonstrations. And so just to sort of stress how this really simplifies things, is here is the input file for a calculation on silicon, and this is everything that you need to do the full calculation from start to finish for these calculations. We'll go into this in more detail in the practical, but also just to illustrate the point that because this is all written in Python, you can actually do all of this within Python as well. You don't even need an input file, it's all scriptable. So here I'm running that workflow, but I've never generated an input file. I'm just doing everything from within Python. I'm just creating my different workflow objects and just calling and running those. Okay, so though that brings me to the end of my talk. So I'll just leave up the take-home messages. I'll acknowledge briefly my collaborators and funding, and I'm very happy to take questions.
Thank you very much, Edward, for this very nice talk. We're running a little bit late, so if you can just give very concise answers to some few very important questions. So one is from Maria Stojkovic. Can you please comment on similarities, if any, between these alpha screening parameters and U value from DFT+U? And could it be that in some limit of Koopman's manifold, for example, going from all orbitals to, let's say, D manifold, we get something that resembles DFT+U? You already showed some comparisons, but do you think that in some limit you can obtain with Koopman's functionals same results as with DFT+U or not?
So it's sort of this, I guess there's two sort of aspects to this. So in terms of there's sort of theoretically and there's practically. So in terms of the theoretical differences, yes, ultimately you could reframe Koopman's functionals in sort of a projector-like formalism and maybe only apply it to select orbitals. And then you might get something that resembles DFT+U. On the other side, practically, we're targeting quite different things in terms of the way that ultimately you calculate these parameters. With Koopmans, we specifically target charge excitations, and so we target band structures being correct. With DFT+U, you target total energies and you calculate these U parameters with respect to charge neutral excitations. So yes, yes and no.
Thank you. So there is another question from Gavin von Witte, a similar question to Maria's one. So since DFT+U+V and Koopman's functionals improve the piecewise linearization of total energy, has it been tested that for Koopman functionals, if it gives the correct material behavior, let's say metallic or insulator, for example, for iron oxide or cobalt oxide that are magnetic insulator compared to a metal in plain PBE DFT. And actually, Ricardo De Gennaro already answered that Koopmans is not yet implemented for metals. And he said that you need to use some other method to open the band gap. Suppose we use DFT+U to open a band gap, cobalt oxide or iron oxide. Then if you applied Koopmans on top, have you ever tried to do that actually or not?
No, it's on the to-do list.
Okay, that's interesting.
But again, I would just sort of stress this point that while DFT+U can improve the band gap, sort of that's really not what it's targeting total energies. And so I'd hope that, the Koopman's correction would be really what we'd lean on to get the total energy differences. On the other side of the coin, if you're starting to think about these systems that contain transition metal elements, we don't have sort of ingredients of like strong correlation. And so, I mean, and there's obviously controversy around DFT+U if the U term really is helping these systems or how important strong correlation is in those systems as well.
Okay. So basically, you think that we can use Koopmans on top of DFT+U?
Yes, I don't think there's any reason why not. It depends exactly how orthogonal the different conditions on determining the different parameters are in terms of the U parameter and because ultimately we're trying to correct piecewise linearity. And so you could imagine that actually this introduces some redundancy because now we can't calculate both alpha and U based on the same criteria. But the subtlety would come in terms of because actually the piecewise linearity condition with DFT+U and Koopmans are different, and so it depends exactly, but they're related, so it sort of depends how different those are. So no, it's an interesting thought.
Okay, thank you. So you mentioned about transition metal atoms. There is a question from Guido Fratesi. What about molecules containing transition metal atoms? See metal porphyrin. I see from the paper First Principles for Emission Spectroscopy and Orbital Tomography in Molecules from Koopman's combined functionals, benchmarks for many molecules, but none of this kind.
No, so exactly. So for the moment, we've sort of stayed away from systems that are canonically strongly correlated. So we impose this additional, well, what we try and cure is this piecewise linearity. And so that is part of the picture for these strong correlation materials, but it's not the total picture. And so while we'd definitely improve results, I don't think that'd be perfect. In contrast, for the sort of, your typical prototypical semiconductors and insulators, there we don't need to worry about these sort of multi-configurational effects. And so we can rely on our Koopman's results a lot better.
Okay, there is another question from Payal Vatva, sorry for the pronunciation. Can we use Koopman functionals in case of time-dependent perturbation? Like if we want to apply a small laser pulse to the solid, then how the charges will excite? Do we have this control using Koopman functionals? Yeah,
so it's time-dependent stuff is super interesting. And this is on the to-do list. So currently it's entirely just like static density functional theory. This is one of the sort of complications with Koopman's functionals that you don't have, say, for example, with Leo Koenig's work. So for Leo Kronik's work, basically you have this criteria for calculating this range separation parameter, but ultimately at the end of the day, they've just got a range separated hybrid functional. And we know very, very well, because of lots of people have done this before, how to sort of use those sorts of functionals in some sort of time dependent TD-DFT code or something like that. For Koopman's functionals, we've got this totally novel sort of correction. And so it sort of takes a bit more work to work out all of these different things. And what I probably should mention is there is work, so just when I'm on the topic of just generally about these sorts of frequency dependent things, and there is work where we've shown that you can use Koopmans in place of GW in a sort of GW plus BSC like work. So it's not, but that's sort of, so that's sort of optical excitation. So it's not quite the same as the sort of real-time laser pulse to a solid, but at least in sort of the, you can do sort of like Koopmans plus BSC to look at these sorts of problems. Yeah.
Thank you. And the very last question from Luis Aguinaga del Hierro. Can we use Koopmans with the phonon code? Or can we compute phonons with Koopmans using finite difference or DFPT?
No, so not presently. So like I sort of just want to stress the point is that what we calculate here and what we correct are primarily eigenvalues. And so like for the Ki functional, it has the same the same total energy and by extension the same forces as the base PBE functional. Now there are, we could think about how our Koopman's correction would affect things like electron phonon matrix coupling, and this is something that we're very interested in and we're going to be working on in the future. But at the moment, sort of the state of the art of our calculations is really we're just focused on projecting very well excellent band structures that are competitive with GW.
Okay, thank you very much, Edward. Thank you all. So now we have 5 minutes of coffee break and then we reconvene. Thank you.